Hello everyone. Following a few weeks of review and of limits, we are now ready to perform our first steps in the world of differentiation or of derivatives. In this video, we are going to focus on the average and instantaneous rates of change of a function. From the onset, let us state that we shall discuss the concepts of average and instantaneous rates of change only in cases where the function is continuous, either on an entire interval or through a point. If need be, feel free to review your notions on continuity that were covered in previous videos. By definition, the average rate of change of a continuous function f over the interval AB is defined as the difference between f of b minus f of a divided by b minus a. We'll denote the average rate of change as ARC and specify the interval over which this average is calculated. Graphically, the average rate of change is actually the slope of the secant line through the points a f of a and b f of b. As you can see graphically, the orange line, which is the secant line, has a change in y, which is calculated by f of b minus f of a, and a change in x, that is the result of b minus a. So essentially the quotient, or the ratio we are calculating, is that of a slope. For instance, find the average rate of change of the function f of x equals 4 over x squared over the interval 1 to 2. Note first of all that the function that we are considering is continuous on the interval 1 to 2 itself. It is a rational function. It does have an issue at x equals 0, but this discontinuity is not within the interval 1 to 2 itself. So the average rate of change following the definition is the change in height, f of 2 minus f of 1, at the extremities of the interval, compared to the change in x, 2 minus 1. We can replace x by 2 and x by 1 respectively in the two expressions at the numerator to find the function's height at those 2 points, and we'll find that the function has actually dropped by 3 units over that 1 unit interval. So a slope of minus 3 is observed for the secant line through the two extremities. Here's what we observe graphically, where in blue we see the function y equals 4 over x squared, and in orange we have the secant line through the 2 points at the extremities of the interval 1 to 2. The slope we have calculated is minus 3, so this is exactly what the average rate of change is depicting. First remark that you probably have noticed from the last picture: the average rate of change gives us a relatively poor idea of how function f actually varies throughout an interval, especially if the interval itself is big. For instance, here we have a function in blue, it's a third degree polynomial, and we've chosen minus 2 to 2 as the interval over which the average rate of change is calculated. So although the secant line's slope is positive and obviously constant, that's not true about the function, which has moments where it increases, decreases, there are moments where it even flattens out for a moment, and there are moments where it increases much quicker than the secant line itself is depicting. So the average rate of change obviously has some flaws. Let's say right away, though, that the average rate of change gives us a very good idea of how a function f varies at a given point if the interval is really small. Here is an example of a quadratic function, and I've already highlighted the point 1, 4 on the quadratic function. Suppose you chose a second point on the quadratic function. Here I've chosen a point where the y-coordinate is 10 and the x-coordinate is roughly 2 1/3. And green, the slope we would find, or the secant line slope we would find, obviously doesn't depict what is happening at 1. It's not the rate of change that the quadratic function has at x equals 1 specifically. But if that second point were moved closer, the secant line now acts or behaves a little bit more at the same rate as the quadratic function does at 1. Still overestimating in this case. But then again, we could also move that point closer and even closer. And the closer the point to the right of x equals 1 is, the better the secant line approximates the actual rate at which the function changes at 1. I could have done the same process from the left, by the way. There's no need for the second point to be necessarily to the right of x equals 1. You probably noticed that in our sequence of operations, what is a secant line is becoming more and more like a tangent line, which would just skim the surface of the quadratic function. So here's our second definition. The instantaneous rate of change of a function f that is continuous on an interval around x equals a is the limit as b approaches a of the quotient f of b minus f of a over b minus a. So this is exactly the process we were depicting in the previous video, where, the magic of PowerPoint here, where point B is highlighted in green, and as we move it towards A, the line is becoming tangent. So the rate of change we're getting becomes an instantaneous rate of change. Okay. Now, of course, this is only true if the limit exists and gives us a finite number. We'll never say that a function has an infinite slope unless we're talking about a point of discontinuity or a point that is not differentiable. Things to be seen in the future. Graphically, the instantaneous rate of change is therefore the slope of the tangent line to the curve y equals f of x at point A f of a. Back to an example we did earlier, we're going to find the instantaneous rate of change of the function f of x equals 4 over x squared, specifically at x equals 1. Once again, remember f is continuous at 1 and around 1 since it's a rational function, and its only domain issue occurs at 0, which is relatively far from 1. Our definition for instantaneous rate of change at x equals a stated that we would like to conduct a limit where b goes towards a and calculate the slope f of b minus f of a over b minus a. Now in our specific case, we were looking to find the slope at 1, so the fixed point we are choosing is 1, and it'll play the role of the a as we move b towards 1. Now f of x was 4 over x squared. Therefore, f at b is 4 over b squared. We are dealing with a 0 for 0 form here that we can handle by simplifying the fractions. So I've multiplied by b squared both the top and the bottom. And then we can proceed by factoring and cancelling. So I've first and foremost factored the 4 from the numerator. And then a difference of squares shows up where we have 1 minus b, 1 plus b at the numerator. At the denominator, I've simply factored out a sign so that a 1 minus b expression becomes common to the one on top. Eliminating the common factors, we now have a limit that is determinate and that can be obtained by direct substitution. So as b goes towards 1, we will get minus 8. Let's see graphically if this makes sense. So here is the function y equals 4 over x squared. The orange line is the secant line we had drawn earlier. We actually had found that the average rate of change is 3. Now focus your attention on the point x equals 1. And you can tell that the function is actually much steeper than minus 3. It's decreasing very rapidly. In fact, we found that the tangent line to the curve would have a slope of minus 8 according to the work we have just done. Alternative notations. So there are different ways of writing derivatives or limits or instantaneous rates of change. The instantaneous rate of change of f at x equals a is usually written as df over dx calculated at x equals a. So this is what we would call the Leibniz notation. Leibniz is a German mathematician who developed the idea of derivatives. More conveniently, we also can write f prime of a. So the prime symbol will be an indication that we had calculated the instantaneous rate of change of the function at a. This would be Newton's notation, which back in the days he called flux. Even in terms of how we evaluate the instantaneous rate of change, different definitions are used. So we've used the limit as b heads towards a of f of b minus f of a over b minus a. Observe how I'm already using the f prime at a notation, so the slope of f at a. You'll also find that rather than using b, many books will use x, and it doesn't matter because in either case we are making that quantity tend towards a. So x is heading towards a rather than b is heading towards a. Graphically, it's the same operation. Finally, there's also this third way of expressing a derivative that is used, or an instantaneous rate of change, where rather than calling the first point or the variable point x, we are calling it a plus h. So essentially it's a point that is h units to the right or h units to the left of a. So it's a slight displacement. And the distance between x and a is replaced by the distance between a plus h and a. And that distance is obviously h itself. So delta x, the change in x, is a plus h minus a, which reduces to h itself. I find that third one leads to a little bit more algebra and more expansion than the first two, but it is quite varied and quite used. So we'll do examples in class where we cover it as well. Finally, in terms of vocabulary, we can interchangeably refer to the instantaneous rate of change of f at x equals a as the slope of the tangent line to the function f at x equals a. Actually, I've already started using the word slope quite a bit even in this video. Sometimes we even cut short and say it's the slope of the function f at x equals a, which will obviously change as soon as we move to another point. More and more, we're going to use the expression the derivative of f at x equals a to represent this instantaneous rate of change. So those are all appropriate ways of expressing the same idea.